back, our first speaker in the afternoon. I hope you all not asleep after lunch. You had an espresso or something. Otherwise, Subhabrata will wake us up about mean field approximations for high-dimensional Bayesian regression.
Thank you so much for the invitation to speak. I've been visiting for a while, and it has been extremely stimulating to be here and to interact with everyone. So I'll talk about some recent work on using mean field approximations to understand the posterior distribution in high-dimensional Bayesian regression. This is based on joint work with Sumit, who is in the audience here today. And so the connecting theme with this workshop is that graphons will come up at some point. We'll have to wait a bit, but they'll come up eventually. But I think one aspect that could be interesting to the audience here is that we try to use this framework of graphons to understand some high-dimensional probability distributions that are sort of main interest. And I think this connection is kind of interesting to me. So maybe it'll spark some conversations in this intersection area. Okay, so I'll try to set everything up from scratch as I go along and won't assume any background regarding Bayesian statistics or the results in the area. And if there are any questions, please feel free to just stop me and ask me questions. Okay, so the general setup for Bayesian inference is that you observe some data D coming from some parametric family of distributions P theta. Theta throughout this talk is some vector valued parameter in P dimensions. And this is what you would really like to learn from the data. So under the Bayesian approach, you assume some prior on the parameter. This reflects your measure of uncertainty. You construct the posterior distribution. And then under the Bayesian framework, you carry out inference based on this posterior distribution. Right? In principle, it's straightforward. But there are, of course, two main questions in this, operationalizing this approach. Of course, from a theoretical perspective, you want to understand what are the properties of these posterior distributions. And this is quite challenging, especially when the parameter space is quite large. So in high dimensions, this is a challenging question. And then there is another very central question, which is, okay, even if you have some control on the posterior distribution, how do you actually work with it, right? So how do you approximate the posterior distribution? Now, the most common method in answering this second question are MCMC algorithms, where you try to sample from these high-dimensional distributions by running an appropriate Markov chain. But I actually will not talk about MCMC methods today. Instead, I'll talk about this alternative approach of variational approximations that has very old roots, but has been becoming increasingly popular in statistics and machine learning because it provides computational, it's computationally very efficient. So what is this approach? At a very high level, the idea is as follows. You have some posterior distribution, P theta given X. You would like to approximate this. So you say, okay, what I will do is that I'll approximate this distribution using a distribution Q of theta from some class of distributions, right? That's the approach. I'll get this good approximation by minimizing the KL divergence. And essentially what this does is that it converts this problem of sampling to one of optimization, although you do this on the space of probability distributions. And depending on what class of distributions you take here, in some cases, this optimization is fairly explicit, or you can get some control on it, right? The most popular choice for this family of approximating distributions is the class of product measures. And we'll refer to this as the naive mean field approximation. This is sort of the first thing that you try. And you can do more sophisticated things. But as a first step, what this is doing is that it neglects the dependencies among the coordinates in your distribution and tries to get the sort of the best product measure.
Sorry, I'm a bit confused. Why do you write Q of theta?
Yeah, I think that's a typo. I think it's just Q.
Okay.
Yeah, thank you. Yeah, that's a typo. We shouldn't have that. Okay.
Another question, do you make some assumption how your distribution depends on the parameter C? Does it have to be smooth, or would I use the even digits for something, odd digits for something else?
Right. Of course, I mean, whenever you have to make sense of whether this works or not, you naturally have to make assumptions on your parametric family. So today I'll just talk about linear regression, where everything is very explicit. But if one has to make sense of this, then of course you will need smoothness in the parameter and things like that. So those will naturally come in, but this is sort of just things at a very high level. Okay, so when you look at this, the first question you think of is that, okay, when is this something reasonable to do? Like, is it meaningful at all to do this approximation? When will it give you some guarantees? And this will form one of the main questions for us today. Now, I think, okay, this is my understanding of the evolution of this line of research in statistics. So I think the way we have tried to address this question in statistics and machine learning is to say, well, we'll understand it in two steps. We'll first develop methods to understand the posterior distribution itself. And then once we understand properties of the posterior distribution, we'll ask the follow-up question, is the naive mean field approximation accurate for that, right? And so we have kind of broken it down into this two-step approach. That has been the typical approach. What we will talk about today kind of flips this perspective a bit, but I'll come to that in a moment, okay? But first, I think, let's talk about the traditional approach that I want to understand when is naive mean field sort of the reasonably accurate. And that will depend on first understanding the behavior of the posterior distribution. So what happens generally? So the classical picture on this is fairly well understood. And this is under the kind of smoothness assumptions that Christian alluded to. So kind of what is understood here is my schematic picture. So here what I have sort of this entire parameter space. Suppose you have data that is being drawn from one particular parametric distribution that is indicated by this red dot here. And it's kind of well understood that if you have a reasonable prior, then your posterior essentially puts most of its mass on a ball of radius 1 over square root n around the data generating truth. Right? And this is all in this classical asymptotic regime where the dimension of your parameter space P is fixed and the number of data points n actually diverges off to infinity. This is the classical asymptotic regime. And it's actually been proved quite recently that at least in this classical regime, if you do the naive mean field approximation, it also has fairly nice behavior. So under these smoothness kind of conditions, it will put most of its mass on a ball of radius 1 over n. Maybe at the level of constants, you'll have a slightly inflated radius, but other than that, in terms of rates, you're okay. So at least in this case, we understand the behavior of the posterior, and we understand that the naive mean field is reasonably accurate. These are okay. So what happens in high dimensions, right? That's sort of one of the interesting questions in modern statistics and machine learning, because you always run into data sets that are high dimensional. And the answer is that over the past decade, there has been sort of quite a lot of work in this area. And the punchline in some sense is that there is a morally similar story that has emerged under additional structural assumptions on the underlying data generating mechanism. Okay. So one of the canonical stories in this regard is if you assume that you have some data generating truth P of theta naught, where the vector theta naught itself has some structure. For example, it might be sparse. Okay. And under these kind of sparsity assumptions, you have a similar story that has started to emerge. You still have your parameter space, you have some data generating truth, and you have your posterior distribution. But now, okay, depending on the complexity of the problem, depending on the rate of growth of your parameter space and your data generating distribution. Your posterior is still kind of supported on a ball of shrinking radius, but this radius size might not be 1/√10 anymore. And that could be essentially, I mean, there is some information theoretic bottleneck here. And in many cases now people understand, what are conditions of the problem so that this epsilon n is essentially the information theoretically optimal rate. There are cases we understand this. Okay, so what I want to do today is to go beyond this regime. So I kind of want to push beyond this, and I want to ask the question, okay, yes.
So, go back to the previous pictures. This is now not for the mean field approximation, but just for the posterior.
Yes, right. Okay, I should also say, but in the past 1 or 2 years, there has also been follow-up work in exploring the behavior of the mean field approximation in these regimes, especially for these sparse models. And it's kind of understood that depending on the complexity of your parameter space, there are conditions where it's still accurate. So it puts most of its mass on a ball of radius order epsilon n. There are also conditions that have, some examples that have been identified where the mean field will actually, put its mass on a ball of shrinking radius, but maybe bigger than epsilon. So it might not be optimal in terms of the rate, but there have been investigations in this direction. But kind of, I think one ingredient that has kind of been very, very crucial in all of these investigations is the a priori fact that the posterior is actually contracting to the data generating truth. That has kind of been universal in all these investigations. So, and that's sort of what I want to push beyond a bit today. So what I really want to talk about is a simple example where you have your posterior distribution that still contains a lot of statistical information about the data generating mechanism, but your posterior doesn't really contract to the truth because you simply don't have, enough signal. It's not non-trivial, but it's not enough that you can kind of overwhelm the noise and contract to the truth. And I'll start with this sort of very canonical example, or very, very simple example that at least to us seems like a good starting point. So I'll talk about linear regression. So the setup here is that you have data yi, xi. Your responses are real valued. Your features are p-dimensional. And to fit the model, you assume a linear model. So you fit the model y = x beta plus error. And we assume just that I have a product prior on the coordinates. So I assume that each beta I is IID from some prior. For simplicity, I'll assume that this variance sigma squared is known throughout. In practice, people put additional priors on sigma squared or estimated in some other way. And I have some technical constraint that I'll assume that my prior is on a bounded set, but I think one can go beyond this if you have like additional kind of tail conditions on the prior. So maybe sub-Gaussian is possible, but for the moment, I'll just restrict to a bounded set. Now, I should make a remark here that throughout this, at least till the very end of the talk, I am not going to assume that this is truly the data generating mechanism. This is really the model that is used by the statistician to fit the data. I am not assuming this is the right data generating mechanism. That will come later. I'll make that assumption, but at some later point. Okay. Any questions regarding the setup? Oh, so I just mean that, okay, this just rules out some, sort of weirdness things where, you can consider your prior is on -1,1, but it's basically supported on -half-half.
I see. So but you don't require that -1 or +1 is an atom.
No. I'm just saying that, okay, this is like the real support. It's not like I can see.
So if I have a tiny epsilon near -1 and +1, and otherwise the support is between 10 to the -6 and -6.
Yeah, that's still. Yeah, that's just a technical report.
X's are fixed here, deterministic.
Yes. So I'll talk about random designs later, but I want to really think about these as fixed designs, and I'll talk about what properties do I need on the design to understand the question. And whenever I assume sort of random designs, I'll talk about properties holding almost surely over the randomness of the design. Okay, so now comes the question of, okay, what did I mean when I sort of say that, okay, I want to go to a regime where there is no contraction, I don't have enough signal, I kind of mentioned these things informally. So let me try to make this a bit more formal. I'll assume that both the number of data points n and the dimension of the features grow to infinity. I'll talk about the relative rates of what I need later. So this is not specifically the assumption that I'll be making, but I think this kind of makes a point. So to kind of think of what regime I'm interested in, you can kind of imagine a setting where your sample covariance matrix has order 1 operator norm. That's kind of one example to think of. I'll kind of weaken this assumption eventually, but this is a good starting point. Why do I want to think of this particular regime, and why do I think of this as a low SNR regime? So for example, if you look at, let's say, the usual ordinary least squares estimate, it has a covariance matrix that's proportional to x transpose x inverse, right? So for example, if x transpose x has operator norm that is of order 1, then if you look at individual coordinates, then its variances are of order 1. So in this case, it's not like the entire posterior is collapsing. Your covariance matrix is something of order 1. And this is sort of the regime that I sort of will be thinking about. I'll make assumptions on the covariance matrix eventually that are of this flavor. They will be weaker than this, but this will always be a sufficient condition for me. And therefore, I mean, in this regime, you can't really recover your p-dimensional parameter consistently, but you can still carry out non-trivial inference, right? So the schematic to think about here is that you have your high dimensional parameter space, you have some data generating mechanism maybe, but when you construct your posterior, your probability distribution is diffuse over the entire parameter space. But it's not like it's uniform. It's still kind of peaked around the truth, and you kind of still want to understand its properties. That's kind of what I want to go at. And the fact that you have this entire diffuse distribution is kind of an effect of the fight between the dimensionality of your parameter space and the number of data points you have. Things are kind of exactly balanced. Okay, so here comes the first question, right? So if you still want to kind of follow the approach that I outlined before, you'll first say, okay, I first need to understand the behavior of the posterior distribution, and then maybe as a follow-up, I'll ask, what is the behavior of the naive mean field? Is it a good approximation? And things like that. But this is where I will flip the perspective. In reality, we don't really, this is my understanding that so far the tools that we had to understand these posterior distributions, they don't really generalize to a setting where you don't have this contraction or where you don't expect this contraction. And instead, we'll basically say that we'll flip the perspective and understand the posterior distribution itself by using the mean field approximation. So the approach that we'll adopt is that we'll develop some sufficient conditions. So we'll carve out a set of examples where the mean field approximation is actually accurate. And then we'll use this mean field approximation to say something about the posterior. That's kind of what we'll do. And I should a priori say that this idea of using the mean field approximation to understand high dimensional distributions, we are not initiating this approach. This has started recently a lot in the area of nonlinear large deviations over the past 7-8 years now. There has been a lot of focus on using this approach to understand questions for large deviations of subgraph counts on random graphs, also in understanding statistical physics models. So our approach here is kind of in this second spirit. So we are thinking of these high dimensional posteriors as sort of models coming from statistical physics, and we are kind of using the mean field approximation just to understand. That's kind of the way we get at this. Okay, so before I go on, I should formalize what I mean when I say that the mean field approximation is accurate for the posterior, right? What do I mean by that? So your posterior distribution is a probability distribution in p dimensions, and things are, every coordinate has order 1 fluctuations. So typically, if you look at the KL divergence, that will be of order p. So we'll say that this naive mean field is actually correct to leading order if this infimum is actually little op. This is precisely what I will mean through the subsequent discussion whenever I say that, okay, this discrepancy is, the mean field is actually a good approximation. So what I will mean throughout is that there is some Q, some sequence of Qs such that the scale divergence is just little. It goes beyond the first order of approximation. Okay, so these are the following things that I want to talk about. So when is it accurate? It is not always accurate, but we'll identify some set of sufficient conditions under which this will be good to the leading order. And I'll try to parse this condition more in the context of random designs. There is a follow-up question that, okay, if this is a good, accurate approximation, can it give you information about the actual posterior distribution? And this is where we'll see graphons can be actually useful. So coming back to the theme of this workshop. And okay, I don't think I'll get to the last part of the talk, which is, okay, what happens if the naive mean field is actually inaccurate? What can you do? So it turns out that there are more advanced mean field approximations that might be better in those settings. I probably might get to it just, or might not, but I'm also happy to talk about that offline. But these are essentially the directions that we're interested in. Okay, so let's jump into the first question, right? So what are conditions on the design that will guarantee that the naive mean field approximation is accurate to leading order for the actual posterior? So to formalize this, I'll need to talk about the normalizing constant of the distribution, or in statistical physics terminology, this would be the partition function for the model. Right? So this is just exactly, you write down what the posterior distribution is, and you integrate it over the prior. This is just the usual normalizing constant, nothing new happening here. The only thing that I did here, this turns out to be useful, is that I had this is a quadratic form originally in the sample covariance matrix. I zeroed out the diagonals and I absorbed these terms into the prior. So I kind of tilted. But other than that, nothing happened.
But the prior is not just some PI.
The prior is, sorry,
so the prior is just one, you could have different pi-i's.
We could have handled that. We considered the case where every pi was the same, but a priori, even if you had different pi-i's, the results would go through. Okay, so this is just, so the reason why I introduce the normalizing constant or the partition function is that there is a very clear connection between the partition function and the accuracy of the naive mean field approximation. And this is, again, not some, this is direct. This is just some algebra once we write out what the KL divergence is, okay? But before I get there, I should recount this well-known fact, essentially from convex analysis, which says that if you look at the log normalizing constant for this model, it essentially has this variational representation, and this is essentially convex duality in this case of exponential families, right? And if you write down what this scale divergence is explicitly, it turns out that, rephrased in terms of the partition function, this basically says that this log of ZP must have this approximation. So I did some algebra here, but this is directly just writing down what this scale divergence is. So the reason why I put these two expressions here is to just develop some intuition for this. So generally, I know that this log ZP can be expressed as the supremum. So if I restrict the supremum to the set of all product distributions, I always get a lower bound. What this is saying is that effectively the difference between the two sides of the bound is essentially something little of P. So this is precisely the condition under which the naive mean field is an accurate approximation. Okay, so here is our result, the first result in this direction, which says that, okay, recall what this matrix A was. The matrix A is the sample covariance matrix in your design with the diagonals all zeroed out. That's what it is. So it's a symmetric matrix, P by P. So I make this assumption. This is kind of the trivial assumption. This is essentially sort of like saying that the matrix A has operator norm of order 1. But this is not the L2 operator norm. This is sort of like the L infinity to L1 operator norm. And so I want that to be ordered P. That's basically just saying that I am in this low SNR regime. That's my scaling assumption. That is not really an assumption about the design. The non-trivial assumption here is essentially this condition that trace of A squared is little o of P. Right? So essentially, as soon as you have this condition on the design, it essentially tells you that the naive mean field approximation is accurate to leading order. Okay. So what does this assumption mean? So if you look at trace of A squared, this is the sum of squared eigenvalues of the symmetric P by P matrix. So it has operator norm of order 1 roughly. So its leading eigenvalue you can think is basically order 1. So what this is saying is that it has little op many eigenvalues that are of order 1. So roughly there are little op many order 1 eigenvalues, then everything kind of decays very fast. So this is one set of conditions under which we can prove that the naive mean field approximation is accurate to leading order. Any questions on the result? Okay, so before I proceed, I should make some remarks about where this comes from. So we use this machinery of nonlinear large deviations that was started in the work of Chatterjee and Dembo, followed upon by Jan and many other people now. Anirban Boschak and Sumit Mukherjee, they used this approach before to understand Ising models on sequences of graphs. And our application in this particular case is similar to that. So just this result by itself is not very different from what had existed in the literature before. And it essentially just stems from the fact that we are looking at a distribution that has pairwise interactions. So as long as it's pairwise interactions, you don't really care if the individual variables are plus minus 1 or if they are in some bounded set. You don't really care. So just this result by itself is not that far removed from what had existed prior to our work. I think the main contribution for these results is to say that you can now take this approximation and actually say something about the posterior distribution. So what I'll tell you henceforth is, I think, our main contribution. But before I proceed, maybe let me pause for a second to see if there are any questions just about this one result.
Can you go back to this so you in the lemma you have this curve divergence to blah blah, and your latest theorem you prove something else, trace of the square of the A is little of P, and your equilibrium is it related? Are you proving then?
Yeah. So I'm exactly proving this, right? So yeah. This essentially is from this rephrasing, right? So right. This scale divergence, that, right? This condition is when it is correct right. Leading order.
Right, you will prove that, right?
I will prove this. This happens if and only if this happens, right? And so they're equivalent. And now so I'll prove that this thing is true under a sufficient set of conditions. So this is not necessarily insufficient, but this is only one set of sufficient conditions under which this will be true. Okay, but now you can ask me this question, okay, is your condition in good? Maybe you're just covering only a small part of this set of examples that exist out there, right? So actually, we have some understanding that there is some sense in which this set of conditions is nearly optimal in some sense. So in particular, if you look at the case of random designs, so if you look at an example where every row is IID from a mean zero Gaussian distribution with some covariance matrix gamma of P, we have, whatever conditions we had trace of A squared little o P, this translates into a condition on the population covariance matrix such that you have accuracy of naive mean field. And this essentially tells you that if you have an IID Gaussian design, for example, then naive mean field is accurate to leading order only if P is little o n. And there are results from statistical physics that suggest, and now we have some proofs of that as well, that if P and N are actually growing proportional to each other, then naive mean field is not accurate. You need more complicated or more advanced approximations, such as the beta approximation or the tap approximation, which will be correct. So in some sense, there are some classes of examples where this is kind of giving you the optimal condition, right? So it can, for Gaussian designs, it can recover this P equals little o n condition, which we believe is kind of optimal. Any questions? Okay, so let me skip over this example. There is another example we had of like a IID Bernoulli design, and we can identify some set of parameter regimes where this is correct, but this is similar. So let me skip this. So coming to sort of the main set of new contributions, I feel, which is, okay, you have this accuracy of naive mean field. Is it any good from a statistical perspective? Does it actually shed, does it actually give you some new information regarding the behavior of the posterior distribution as a whole? Okay, so at a high level, my answer will be yes in certain cases, but let me expand more on that, right? So you will need some additional conditions under which you can say what things will. Now, okay, I put in a lot of notation here, but I don't want you to look at it. This is no good. I'll try to tell you what the punchline is. But before I do that, maybe let me make a remark about Ising models on complete graphs or Curie-Weiss models for people in the audience who might know this example. So for example, if you look at the Curie-Weiss model, then it is well understood that naive mean field is accurate in this case. But if you look at the low temperature behavior of the Curie-Weiss model, for example, then you have two of these phases that exist, right? You can have coordinates roughly like plus m star, the other ones having a minus m star kind of bias, right? And if those are the examples that you have, then, okay, in that particular case, you can identify that it's a mixture. But generally, you can have many of these phases that can coexist. And so extracting information out of that becomes a bit challenging. So what I'll describe in the next few slides are further sufficient conditions under which you just have one dominant phase so that you can actually extract information out of it. This is kind of the simplest thing you can do. And you can definitely push this forward, but this is just to illustrate that there are conditions under which you can extract information. And in case this example was unfamiliar, please feel free to ignore my remark. So let me.
So with this example is familiar to me. So you're saying essentially your results will hold in the high temperature regime?
No. The result holds at any temperature. The point is that in certain cases, like the Curie-Weiss example, at low temperature, you can have multiple phases, right? And so in more general complicated examples, your number of phases could be pretty large. They could in fact be like e to the little o p many phases. So in those complicated examples, it's difficult to derive the properties of the distribution using the mean field approximation. So what I'll do is that I'll avoid that issue altogether, and I'll identify further conditions, such as the high temperature phase, under which there is one dominant phase, and using that phase, I will get some information about the posterior.
That for me would still be, as a physicist, I would call that a high temperature regime. So you will have one dominant phase.
Yeah.
And then you can.
Then I can extract information. So it turns out, I mean, from a purely statistical perspective, I think it still sheds some information, because among the conditions that I'll talk about, you can have high temperature conditions, but you can also put in conditions on the prior, which will still govern, which says that the model is basically at high temperature in any case. So for example, Sumit has follow-up work with other colleagues where they show that if the prior is log concave, it's always fine. There's always one dominant phase. Yeah.
I'm not sure I understand why having multiple phases is such an obstruction, since if it's your product distributions and you match one of them with the best one, then the convergence is just a log of the number of things.
Yeah. Agree. It's still true, but it's just that because we are only looking at things at the resolution of little op, it's exactly as you say, you can have e to the little op many phases, and so kind of match, like extract. So I think things can still be done non-asymptotically, but kind of taking limits out of that turns out to be a bit more hair. So I agree that it's definitely possible to go beyond what I'll describe here, but kind of going to the most general setting, I still think is a bit more difficult. So, yeah.
Your optimization in the model, I blah blah optimize the I star, right, to digest your slides and it's going through.
Okay.
Then it's particular value QI star.
Yes, QI star.
Expectation.
Yeah.
Right.
Right. So the punchline is that for this very special case of linear regression, there is something special that happens. For any product measure that is an optimizer, you can basically prove that the coordinates can just be quadratic tilts of the prior. That's special about the linear regression case. And once you know that, you can identify sort of what are these parameters, gamma 1i and gamma 2i that give you the optimizers. So what the main punchline that I would like to kind of, I would like you to take away from this slide is that for this very special case of linear regression with product priors, you can convert this optimization problem over probability measures to a scalar optimization problem. And that this is special about linear regression. You can do this, and essentially it comes down to still a high dimensional optimization problem. This is generally non-convex, but at least it's a scalar problem, not on the space of probability distribution. That's kind of the big takeaway from the slide. Okay. And okay, so this is what I meant formally, when I was talking about this one unique phase kind of thing. The point is, if you now look at this optimization problem, if it happens that you have some u hat, such that if you move away from u hat by distance order p, then the optimized value essentially falls off from the global optimum. Then this point u hat essentially determines the properties of a sample drawn from this distribution. Let me parse that a bit more. So suppose you have this condition, right? And you have some u hat which satisfies this condition. Then if you draw a sample beta I from the posterior distribution, and if you look at properties at the scale of law of large numbers, then you can describe it essentially in terms of this u hat. There is an explicit set of distributions that you can derive out of u hat, which essentially tell you the law of large numbers type properties for samples drawn from the posterior distribution.
And what mostly the condition says?
Yeah, so this is the condition. So the condition essentially is that you have some u hat here, so that if you move away from the u hat, then the value essentially falls off. Okay. It doesn't really say that I'm not assuming that there is one global like there is only one. Like I'm not assuming this function is convex or anything, or convex or concave. It can have different local optimizers, that's fine. But in some sense, I'm just assuming there is one roughly unique dominant global optimizer. Yes. Oh, 5. Yes, I will wrap up. Okay, so as promised, okay, so there are some conditions which I kind of mentioned. So if you have, this is sort of a high temperature kind of condition on the model, which governs there is one unique phase. You can put in some conditions on the prior as well, I'll skip over this for the time being, but you can interpret these conditions, and these tell you, these are conditions under which you have one dominant phase. But okay, let me talk about graphons, because this is a workshop on graph limits, and I want to kind of convey how these can be useful in understanding these posterior distributions. So far, in whatever I have done, I have stayed away from making assumptions on the true data generating distribution, right? I have worked under a case where y and x are given to me, and I work with that. But if you look at the literature on Bayesian statistics, the de facto approach is to assume that there is some underlying model which can be different from the model that you fit. But then you try to see how much of the truth you recover. So that's kind of the usual approach. You assume that there is some model which generates the data. As the statistician, you don't quite know what that model is. You fit something else. And then you want to know, okay, how do I do? So I want to kind of take a step now towards this approach and see what this set of tools can actually tell us about this particular setting. So I have some stuff on graphons. I think this is very well known to the audience here. We saw some of this in the earlier talks today, so I'll skip over this and I'll just talk about this one result. So what this is that now suppose your data is actually generated from a true linear model with mean x beta naught, right? I'm not assuming that the coordinates of beta naught are IID or something. This is just some vector sequence of vectors beta naught. I'll make now assumptions on the convergences of these of my problem parameters. Okay. So in particular, I'll assume that if you look at this sequence of matrices AP, recall that this is just the sample covariance matrix with the diagonal zeroed out. Blown up by P, this converges under a strong cut metric to some limiting graph on W. And I have L1 convergences for other functions. This is precisely what you'd expect. Then under this mean field sort of assumption, I can actually state a limiting variational problem for my log partition function or for my mean field approximation to it. This is sort of the main punchline. And then I have some description for this limiting functional. I have some interpretation for that, but I don't think I'll have time to actually parse this. So there is some explicit form for what this functional is. But what is nice here, and this is kind of what I want to draw your attention to, is that under these conditions, you have some unique optimizer. This unique optimizer has a fixed point description. And this essentially governs law of large number type properties for samples drawn from the posterior distribution. So this is sort of where this limiting description turns out to be useful for us. And I think this is what connects it to the themes of this workshop. So I had some other things that I'll skip over to not go over the allotted time. So takeaway essentially is that we can use this theory of nonlinear large deviations to actually justify using naive mean field approximations. They can tell us about high dimensional Bayesian posteriors. I had some stuff later, but I didn't get into that. There are some follow-up directions, but I'm happy to talk about it more offline. Thank you so much for your attention.
While Julia sets up, maybe we have time for a question.
I can carry it to whoever wants to ask me questions. Yeah, sorry, I had quite a lot of notation on my slides.
I don't know if I understood everything correctly, but is this well understood that the mean field approximation is far easier to compute in high dimension as well?
Right. So if you are in like these high temperature sort of regimes, then you actually have sort of global convexity and things are nice. Turns out there are similar conditions actually even under these conditions on the prior that I sort of described. So there is a result that Freddie Kohler has from a few years ago that is actually very interesting, where he says that for ferromagnetic easing models, if you start from the all ones configuration, you will get always to a near optima for the naive mean field, irrespective of whether there is a unique phase or not. But we didn't make any such ferromagnetic assumption in the model. So in the case where you're away from these assumptions, it's generally non-convex. So without additional assumptions on the design, it could be hard.
Okay, if there are no further questions, maybe we can start with Julia.
Thank you very much for the organizers for inviting me to this workshop. It's been very enjoyable so far.